Okay, I guess I'll get started. So today we're going to see faster flow algorithms, faster max flow algorithms. Okay, so we're going to see scaling, blocking flows, like this, blocking flows, which you can speed up using link cut trees. Okay. So let's just remember where we left off last time. I assume that people, either had seen some flow or will just look up details on what I said last time. But the basic idea of last time was we have a capacitated directed graph, G, which is VE, and each edge, E and capital E, has some capacity CE, which I'm imagining is in the range from, it's an integer in the range from 1 up to U. Okay. And we'd like to find ST flow of max value. Okay, so you remember that a flow for us has to obey the capacity constraints. First of all, a flow is just a vector defined on the edges. Okay, it should obey the capacity constraints. We shouldn't push more flow than an edge has capacity for. And the value of a flow is just the amount of flow coming out of S, right? So we said that the amount of flow going out of S has to equal the amount coming into T, and for every other vertex, flow in equals flow out. Total flow in equals total flow out. Okay, so what I said last time was repeatedly find augmenting paths in residual graphs. Right. So remember, if we have some current flow F, you can define what's called a residual graph, where the new capacity in the residual graph is the old capacity minus the flow on that edge. Right. So the residual capacity is just how much more capacity is left over given the amount of flow we've already sent. Yeah. Oh. Okay. No question. Sorry. So you can show that this algorithm is correct. The algorithm of find an augmenting path. In other words, find some flow. Then define the residual graph. Find an augmenting path there. Define a new residual graph, etc. Keep iterating until there is no augmenting path. That is a correct algorithm. Okay. So Ford Fulkerson, you just repeatedly find augmenting paths. Each new path pushes at least one more unit of flow. And time to find one augmenting path is just linear in the number of edges. Why is that? How do you do that? Just say 3 letters or 1 word or something. Yeah, yeah, DFS, depth first search, DFS, BFS. Basically, just find any path from S to T in the residual graph and push one unit of flow there. So this implies the time O of M times F star, where F star is the value of the optimal, is the max flow that's achievable. Okay. Okay, so today we're going to talk about basically other algorithms that get faster than this. Okay, this is pretty terrible. I mean, F star could be as big as, for example, N times U, right? The amount of capacity coming into T is as big as N times U, or N minus 1 times U. It's not even polynomial, right? Because when we talk about polynomial time, we want polynomial in the representation of the problem. And to write down a capacity which is up to U takes log U bits, whereas we're spending, we could spend up to U time, right? So that's exponential time. Okay. So, so time terminology. So we say the algorithm is weakly polynomial. That means the time is poly m and log of u. So I mean, it is polynomial time in the representation of the problem. But we say it's strongly polynomial if the time is simply poly m. The running time doesn't depend on the capacities at all. I mean, it implicitly does in the sense that you have to pretend that you can manipulate capacities in constant time. You can take mins of those numbers and add them and stuff in constant time. But the number of steps of your algorithm shouldn't depend on how big the capacities are. Okay. And the last thing, which is I guess worse than these two, is pseudo-polynomial. And this is poly m and u. So Ford-Fulkerson is pseudo-polynomial. Today we're going to see some strongly polynomial algorithm, and we're also going to see a weakly polynomial algorithm. Okay. Questions about anything? And another place, for example, where you've seen pseudo-polynomial is knapsack, right? So if you remember the dynamic programming algorithm for knapsack, the running time, not the p-task or fp-task, but the exact algorithm, you do a dynamic program where the number of states involves the total weight of your knapsack, right? So you have your time is linear in the total weight of the knapsack, but that's again not actually polynomial time, right? That's again that's what you would call pseudo-polynomial. Okay. So before I start covering some algorithms, I want to tell you what's currently known. So best known, and there have been some improvements recently, despite there not having been improvements for like 30 years beforehand. So from the strongly polynomial, the best known is O of mn time, and this is due to Orlin. Okay, this is in stock 2013, so that's fairly recent. In fact, today I'm gonna show you a lot of the steps to get almost this. I'm gonna show you mn times log n. There's gonna be an extra log n. Okay, I don't know if I'll get to show you all the details of log n, but you'll see at least log squared n. And that bound is from 1983. So, over the course of 30 years, finally the log n was removed. Actually, there was something in between where the log n was improved to something that is never bigger than log n, but it can be better if the graph is very dense. It might have been, like the base of the log changed to something maybe like n squared over m, right? So if the graph is very dense, then, wait. Okay, I forgot what the base of the log was. But basically, 30 years of log n got shaved. Okay, so from the weakly polynomial point of view, we have two algorithms, neither of which is strictly better than the other. So one is O of m times the min of m to the 1/3 n to the 2/3 log of n squared over m times log u. Okay, so right, this is a little better, right? So this is mn. This is like mn to the 2/3 times some log factors. This is due to Goldberg and Rao. And more recently, we have an algorithm that takes time O tilde m times square root of n times log squared u. And this is Lee and Sidford just like a month ago, or less than a month ago. Interior point, the faster interior point, and it's via the interior point method. Okay. Right, and this tilde is hiding some log factors, like some log m's, for example. Good. But in the worst case, if you think about it, in the worst case in a very dense graph, m could be as big as n squared, in which case this min could be as big as n to the 2/3. So this would be like m times n to the 2/3 times some logs, whereas this would be m times root n times some logs. So there is a regime where this algorithm is better, but neither strictly dominates the other, right? If it's a very sparse graph, if m is much less than 2/3 into the, I guess less than n to the 3/2 maybe, right? If m is much less than n to the 3/2, this will be much less than m root n, in which case this would be better than this. So there's some regime where one's better than the other. And there are also some other things you can do for unit capacity graphs. Okay, so there's a 1975 paper of Evan and Tarjan that shows that you can basically get this bound without these two logs, or these these two logs in unit capacity graphs. Okay, that's Evan and Tarjan. And you can also get m to the 10/7 in unit capacity graphs up to logs, and that's due to Maudry in Fox 2013. Okay, so this is kind of this is the state of the art. Well, okay, so except here, yeah, okay, good. Is m to the 1/3? Oh, you're saying m is at most n squared. Yeah. Yeah. Sorry, you're very right. Okay, good. Okay. Yeah. Yeah. Sorry. Okay. Yeah. Okay, good. Yeah.
So in the strongly polynomial case, you said you still have to include the time to do basic operations, right? Like it will take log u time to do comparison.
Wait. Go back here. Wait, sorry. I think this is actually 1/3, but wait, I'll come back to you for a second. Why did you say this? Or?
I don't know. I just probably already, but maybe.
Okay, so I'll fix it. I wrote down this, and I thought it was this, but I could be wrong. So, yeah, I'll fix that in the notes, whatever it is. Okay, so what were you saying?
Oh, so it seems like the strongly, like there's no reason to use the strongly polynomial case because you still have to multiply it by log for the number.
So I'm assuming, right. So I'm assuming I'm operating in the word RAM model, and my words have at least log u in size. Okay, so I can do arithmetic on capacities in constant time. That's my assumption. In which case, in the word RAM model, like those are the running times. Oh, did you find it? m to the 2/3? Did I really mistype it that badly? Okay, well, okay. Sorry for lying to you. Okay, so, no, but that seems, really? That doesn't seem to make sense, right? Because then this would be better than this. So I'm just going to put this for now, and I'll fix it in the notes. Okay, so there's some powers here that I'm forgetting. Okay, so now let me just explain to you scaling and blocking flows. Okay, so the idea behind scaling algorithms for max flow is that we're basically going to reduce general capacity case to the unit capacity case. No.
The original paper says I do the 2/3.
Oh, it is 1/2 and 2/3?
Yeah. M to the 1/2 and
I see. So my 1/3 here was off. Okay, good. Okay, so the general idea of scaling is to reduce the general capacity case to the unit capacity case. Okay, and how do we do that? So treat capacities as log base 2 of u bit integers written in binary. Okay. And then this is how the algorithm is going to go. Start with F being the 0 flow. And all capacities 0. Okay. Now what do we do? For k, let's say, equals log base 2 of u minus 1 down to 0. Double each capacity. So for each edge E, double both the flow on E as well as the capacity of the edge E. Okay. Also, for each edge E, double both. Let me see. Start with in all capacities. Let's call this C prime of E to be 0. Okay, so there are some actual capacities in the graph C of E. Okay, but we're going to maintain capacities C prime of E. Okay. Initially, the edges have no capacities. So their C prime value is 0. And then basically what we're doing here is we're shifting in bit by bit the next bit of the capacity of that edge. Okay, so we imagine that so like the edges have various capacities. How should I put this? So let's say the edge capacities, one has capacity that's 0, 1. That's 2 plus 4 is 6. This is like capacity 6. Another one has some capacity 2 plus 4 is 6 plus 8 is 14, etc. So initially, all the edges have, and let's say let's put leading bits of 0 everywhere. Initially, we imagine a graph where each edge capacity C prime is 0. Okay, and then what we do is we shift in the next bit of capacity. So now these three edges will have capacity 1, and this edge will have capacity 0. And then we'll solve a flow problem on that. I'm going to continue writing. And then once we do that, we shift in the next bit of capacity. So now this has capacity 2, 3, 2, 0, right? And then we do that bit by bit until finally we have the entire capacity. Okay, C prime will be the entire capacity at the end. But so that's roughly what's going on here. But let me finish this pseudocode. So for each bit of the capacities, starting with the most significant bit down to the least significant bit. So we currently have some flow in the current graph defined by the C prime capacities. We're going to double all those C primes, which means basically, right, this used to be, when we were here, this used to be the least significant bit, but then we shifted over one to include one more, which means this position got shifted over, which means the capacity doubled. And then we're going to double all the flow values, right? So they're going to remain feasible because we doubled the capacities as well. And then we're going to add these in. So for each edge E, add in the kth bit of CE to C prime E. And now, augment, keep augmenting F until it's a max flow. Okay. So the invariant we're going to maintain is that every time we enter the start of this loop, the flow we have is a max flow for the current capacity C prime that we have. Okay. So how about correctness? So we maintain the invariant that F is always a max flow for the C prime capacities at beginning of loop. Which is definitely true in the beginning when the capacities are 0. Okay. And why is it true from iteration to iteration? Well, I guess I already said this, but the point is when we double the capacities, right? So to be a max flow, we know max flow equals min cut, and we know a max flow in particular saturates a min cut. Okay. For a flow to be maximum, there must be some ST cut that has 0 residual capacity across it. So look at that cut after this step. We've doubled the capacity of that cut, but we've also doubled the flow across that cut. So even afterwards, it's still a max cut. I mean, it's still a max flow. Okay? And then we added in this extra bit of capacity, potentially, to some of the edges. Right? So, but we still have a feasible flow. It's not a max flow, but it's still feasible. But we know that if we have a feasible flow that's not maximum, we can keep finding augmenting paths to make it maximum. Right? So this will find us the new max flow. Okay. Okay. So how about running time? The running time is basically the number of iterations times the time per iteration. So the number of iterations is pretty clear. It's written explicitly. This is just log u. How about the time per iteration? Yeah. So what is the time to do the unit capacity case, which I've written here, I guess. So, but here, what's f star? I'm sorry? M. Why M? So I mean, okay, so the thing is, when we shifted in this new bit of capacity, right? When we shifted in this new bit of capacity, there might have been some unsaturated edges. Those got doubled, and then we added this new bit, right? So it's true that there are at most m edges, but they're not all going to be unit capacity edges, right? Do you see what I mean? Right. So it's not simply that we're in the unit capacity case. I shouldn't have said that. Okay. But we want to argue that this value f star is small. Right? So right, we're not in the unit capacity case, but we want to say f star is small so that Ford-Fulkerson is pretty quick. So
You look at the cut
yeah.
at the beginning of the phase,
Yeah.
the value of this cut increases by almost 10.
Yeah, exactly. So that's the point. So let's look at ourselves right here. We've doubled the capacities, but we haven't shifted in the new bit yet. Okay. This flow F is a max flow for the current capacities, right? Which means that there's a cut that's saturated. So that cut has 0 capacity across it. And then we added in the next bit of capacity to some subset of the edges. The worst case is that, any cut is always an upper bound on the max flow. So let's look at this cut. There are most m edges involved in this cut. It had capacity 0. We've added at most m capacity, at most 1 capacity per edge to this cut. So this cut now has capacity at most m, which means the max flow value is at most m. Right? So this is O of m times f star, which is O of m times the min cut, the min ST cut. Right? And the point is, before adding in the next bit of capacity, some cut was saturated. Was saturated by F and has 0 residual capacity. Let's call this cut C, some cut C. Do I have a scribe for today? Oh, you're scribing, good. Right, so some cut C has 0 residual capacity, and C has certainly at most m edges, implies after shifting in the next bit of capacity, the residual capacity of C is at most m, which implies that the min cut is at most m. Right? So overall, this thing we're saying is O of m squared. So this thing is O of m squared log u. Okay. Yeah. Okay, so that's scaling. And we're going to see scaling again soon, but before that, I want to now move to blocking flows. It turns out you can combine them. You can use scaling on top of blocking flows. We're going to see that. Right? I mean, basically, you can use scaling in combination with lots of different algorithms, right? Because scaling just says you reduce to having to do this over and over again, right? So you could imagine instead of doing Ford-Fulkerson here, you'll do some other algorithm, for example, blocking flows, which we're going to see now. Okay. So blocking flows. How's that going to work? So in a residual graph, GF, okay, we say the level L of V is the shortest path distance from S to V. Okay. By the way, before I get more into blocking flows, I just want to say that if you do, right, so Ford-Fulkerson doesn't really specify how to find the augmenting path. For example, you could do depth first search. You could also do breadth first search. You could also do what's problem 1 on the current P set, which is augment along the path that has the largest minimum capacity. Okay. And depending on how you find augmenting paths, you can get different running time bounds. So what you're going to see on the P set is that you can do a lot better than vanilla Ford-Fulkerson if you augment along such a path with a large minimum capacity. Okay. Or another thing you can do is instead of depth first search, do breadth first search. And you can show that you'll get a bound of m squared times n if you do that. Okay, so that's Edmund-Karp. What I'm going to show you now is that m squared n, you can actually get m times n squared using a different technique via blocking flows. But I wanted to find, let me go through exactly how that technique works. Okay, but were there questions at all about scaling before I do blocking flows? Yeah.
So it wouldn't work if you had any fractional capacities, right? You couldn't do this.
Yeah, so I'm always assuming that the capacities are integral because you can always clear denominators. Yeah. Yeah, I mean, otherwise, right? Otherwise, kind of log u doesn't really make sense as a bound if they can be fractions because, you could say, well, I mean, what is u then? I guess u then would be the ratio of the largest to the smallest, maybe something like that. I mean, if you
The size after.
right, yeah. So that's if they're integers, right? But if you say they're fractions, then okay, why can't I just take all the capacities and normalize by the largest one? That doesn't change the flow problem at all, but that changes the largest capacity, right? So something about that is off. So you need some kind of normalization for it to make sense. Okay. Yeah, so I'm assuming all the denominators are cleared out. Okay, so let me move on to blocking flows. Okay, so let me make a definition. So the level of a vertex in a residual graph is the shortest path distance from S to V. And an edge UV is admissible if basically the level of V is the level of U plus 1. So we're only allowing edges that are along the shortest path, basically, from, let me write the last thing. A path is admissible if all its edges are admissible. Okay. And a blocking flow By the way, I believe I want to give the citation for blocking flows. Didn't write it down, but I believe it's Dönitz. Sometime in the 70s. Okay. So a blocking flow is an admissible flow i.e. it decomposes into augmenting admissible paths such that every admissible is an admissible flow, let's call it F, such that every admissible path, ST path, has at least one edge saturated by F. Okay. So, just as a toy example, let's pretend that this is our current residual graph. And let's say all these edges have unit capacity. Okay. So which of these edges are admissible and which edges are not admissible? Yeah. Yeah, so this edge here is not admissible. Okay, and one example of a blocking flow is, well, certainly this max flow is certainly a max flow is a blocking flow. So one example of a blocking flow is that green flow. This is a blocking flow. So okay, so a question for you. Do you believe that the claim that kind of a blocking flow is just a specific kind of, so a max flow is definitely a blocking flow. Maybe a blocking flow is always a max flow. So really finding a blocking flow is the same as finding a max flow. Do you believe that claim? No, you don't believe it? Okay, so anyone have an example in mind? I guess maybe it would be a little tough to come up with this right on the spot, but of why a blocking flow might not be a max flow. Yeah. SU, UV, V2. But then UV is not admissible. So a blocking flow for me should decompose into augmenting admissible paths, right? So it should only use admissible edges. If you use the edge UV.
So if you have the same blocking flow,
yeah.
it's one, but now with capacity, we change the capacity of these edges.
Oh, you want to use this graph?
Yeah.
You want to use this flow?
Yeah, but then we change the capacity.
Okay, so what do you want the capacities to be? You want what? SU to be 2, UV to be 1, VT to be 2, and the others are still 1? Okay, so this green flow, I guess, only has room to put 1 on it, right? Okay, so is this a blocking flow? Yes, it seems that it is a blocking flow. And is it a max flow? Ah, yes. Yes, that's true. Yeah. Right. Yeah, and you can even come up with examples. You can even come up with examples where all the edges are unit capacity. So if I just change the graph slightly, let's say that. Right, so let's make all these unit capacities. Then this flow is a blocking flow. Right. And it's certainly not a max flow. The max flow would send one along this way, one along that way, but kind of this flow kind of blocks both possibilities. Okay. I mean, the only augmenting paths, I guess, are this one, and this one, and they're all of them have at least one edge saturated. But yeah, that's a good point. That's another one as well. So questions about what a blocking flow is. Okay, so first, let's analyze when all edges have unit capacity. Oh, actually, before we do that, yeah, before I do that, let me write down a claim. After augmenting, and this claim is really the point of finding blocking flows. Okay, so after augmenting along a blocking flow, the shortest path distance from S to T in the new residual graph or in the new, say in the new level graph, i.e. the graph containing admissible edges, strictly increases. Yeah, these are edges that have residual capacity. If they have zero capacity, we ignore them. These are edges that have residual capacity, and they have to increase the right. They have to. It has to go from a vertex that's closer to S to a vertex that's one farther. So, okay, before we prove this claim, how would you use this claim as part of an algorithm? Well, oh yeah. Say it again. Say it again.
Each time you decrease the simulation t,
You increase the
distance
by one, yeah, by at least one.
So this can be more than.
Yeah, you can't do it more than n times, right? So yeah, that's the point. So the point is, right? These are when I say distance, this is an unweighted graph, right? So the distance between S and T certainly can't be more than n if there's an augmenting path at all, right? If it's more than n, that means it's infinity. That means there's no path. In which case we're done. We're done augmenting. So consider the following algorithm. Find a blocking flow and augment along it. Now form the residual graph. Find a blocking flow there, augment along it. And just repeatedly find blocking flows in the residual graph and augment. The number, oh yeah? Yeah.
then our next augmenting path would have to go backwards along some of the edges, right?
Yeah, that's fine. Yeah. Yeah, augment in general in the residual graph, some edges get reversed.
Well, are they still admissible?
Are they still admissible?
Are the reversed edges admissible?
Oh, so the definition of admissible is that this happens in the current residual graph. So you look at the distance from, so the residual graph changes in every step.
Yeah.
So so what's admissible and what isn't is a function of the current residual graph.
Yeah, but in the new residual graph,
Yeah,
after you've done that,
yeah.
there won't be any. I mean, it's disconnected, right? Unless you include those backwards edges.
Maybe I'm, so, okay, so,
But that's not the next flow.
okay, hold on. So you want to take this graph and you want to form its residual, right? So, so let me pause for a second. Let me just draw that graph here. So let me, 1, 2, 3, 5. So now what are the residual capacities or residual edges? So you have, so we had before, so this stays, this goes this way. This goes this way. This goes that way. This goes that way, this way, this way. And here you go, this goes reversed. Right? This is the residual graph. This is GF, where this is my flow F. Right?
Ones you reversed actually have zero capacity now, right?
Well, remember the definition of residual capacity, right? It's the old capacity. It's the capacity minus the flow value. So if you had capacity 0, and remember I'm in that definition from when we were talking last time, I said if I have flow pushed the other way, I view that for the purposes of forming the residual graph, I view that as kind of minus flow on this edge, right? So 0 minus -1 is 1. So now I imagine that this has, there's a capacity 1 edge this way, there's a capacity 1 edge this way, there's a capacity 1 edge that way, right? And then now the shortest path distance from S to T, I think is 1, 2, 3, 4, 5, length 5. Actually, I think that this is the only ST path, right? So the level graph, let me define this as, let me label some vertices as A, B, C, D, T. So the level graph would actually just be a path. It would have S, A, B, well, S, A, B, C, D, T. So S, A, B, C, D, T. Right. That would be the level graph corresponding to that blocking flow. And then there's only one augmenting path here anyway, so you would just find it. All right. Questions? Okay, so the point was, as you said, the number of iterations. So if we have this algorithm that does the following: find a blocking flow, augment, find another blocking flow, augment, etc. The number of iterations can be at most n until there's no more blocking flow, right? Because the distance keeps increasing between S and T. So the running time. So this claim would imply that the running time is at most n, O of n, times the time to find a blocking flow. Okay. And we're going to show that you can do this in unit capacity graphs in linear time, basically, in time m, by basically a modified depth first search. You can also do this in, we're going to show that you can do it also pretty simply in general capacitated graphs in time mn, in which case you get a time of mn squared. using a fancy data structure, namely link cut trees by Slater and Tarjan, I'll show you a little bit about that. You can actually do this in m log n for a capacitated graph, in which case you'd get a time of mn log n, which is not too far off from what I told you the mn time just last year's stock. Okay. So really, we just need to prove this claim, and then we need to understand the time to find a blocking flow.
So what did the stock paper use to do something
Oh,
similar to this?
I think that paper is pretty complicated. Actually, I haven't read it, so yeah, I'm not sure. I'm not sure. Since yeah, I'm not totally sure what Orland's algorithm is doing. Okay. So let's prove the claim. It's actually a pretty simple claim. So let's look at the level graph before augmentation is L, and the level graph after augmentation is, let's call that L prime. Okay. The level graph, remember, is the graph containing the admissible edges. So what does L look like? Well, here's S. And basically, you can organize it right into the distance from S to T. So there's some at distance 1, there's some at distance 2, and there's T over here. There's some edges. And then there's only edges in between adjacent layers. Right. And what is a blocking flow? A blocking flow just is some flow that decomposes into a bunch of ST paths here. Okay. And so let's say, let me also draw some other edges. Question. So this is a subset of the edges in the residual graph, right? The ones that go from one level to the next. Is it possible for me to have this edge? So not all the edges are drawn here. Is it possible for me to have an edge that looks like this? Or an edge, basically edges that skip layers? No, right? Because that's the definition of shortest path. This means that there's actually a shorter, well, this is okay, this is an adjacent level, but this is not okay, right? Otherwise, this would have had a shorter path to it, and it wouldn't have been in this level. So I can't have those kinds of edges. What I can have is I can have edges going backward and possibly jumping, possibly jumping levels too. I could have an edge that goes all the way back here, for example. That's possible. So if you think about what kinds of edges are possible in L prime, the only edges allowed, the only edges that appear are either from L. Okay, so certain edges from L might appear. I'm not going to rule them out. We might also have some edges show up from the reverse of L, namely a reverse of one of these edges, right? Because after we augment along paths here, some of these edges might get reversed, just like what you saw in that example. From L or rev L, or yellow edges, going backward. Right?
The yellow edges are not in L, right?
They're not in L because they don't go from one level to the next level. But they might be in GF, in the residual graph. You had a question? Oh, yeah. You could have that. You could have edges in the same level. That's true. Okay. So what does this imply? This implies that the shortest path distance in L prime between S and T is at least the shortest path distance in L from S to T. Right? If you imagine looking at this graph and you're trying to get from S to T as fast as possible, it doesn't ever help you to take a yellow edge or to take a reverse of one of these white edges, right? Okay. So, okay, good. So the question is, can dl prime st equal dst? Okay. And the answer is no. Why is it no? Yeah. Right, yeah. If the shortest path distance in L prime were the same as in L, that means all the edges in that shortest path would be L edges. Right? That means we have a path of, that means that there's a path in L prime which also exists in L. But by definition of blocking flow, at least one of the edges on that path has to have been saturated. Right? So that entire path cannot possibly be in the new residual graph. So it wouldn't be in L prime. Right? So if there is a length dl st path in L prime, then all those edges are L edges. Implies at least one is saturated by our blocking flow. So this is a contradiction.
They all have to be L edges by definition of admissible. Is that
right. So the claim is that right. So if you didn't use only L edges, if you use some yellow edges or some reverse edges, then that would only increase your distance. That would only increase the length of the path. Right? So if you're telling me that your path length is exactly the shortest path length, then you have to be using L edges. Okay. So that's that. So how do we find a blocking flow? So finding a blocking flow. So let's first look at the case of some special case. Let's look at unit capacity. Okay. So we're basically going to do some kind of modified depth first search from S, or repeated depth first searches. So I'm going to have three types of operations, which I'm going to call advance, retreat, and augment. Okay, so this is defined, right? This is going to be on the level graph. remember, I'm trying to find a blocking flow that uses admissible edges. Okay, so this procedure, I'm going to run it on the level graph. Okay. So let me have a loop here. So let's say while true. So let me think about how I want to say this. So I'm going to say V is going to get set to S, our current vertex. And then I'll say while true advance. So while V has some outgoing edge, let's say VU, I'll advance. And by that I just mean that V goes to U. So we move to vertex U. How should actually let me sorry, I shouldn't have written it this way. So let me say this. So we'll always have our finger on some vertex V. That we got to by DFSing starting from S. Okay. If S is equal to T, if V is equal to T, so if we've managed to reach T, then augment along the ST path we found then delete the zero capacity edges. Okay, so I'm going to describe the algorithm in the general capacity case. Okay, but of course, if we're in the unit capacity case, then after augmentation, all of those edges have zero capacity now, so we would just delete all of them. Okay, so if V equals T, augment along ST path we found, then we put our finger back on S, put finger back on S. Otherwise, if V is not equal to T, advance to some edge U, to some vertex U, such that VU is an edge. Of course, there might not be such a U. We might be at a dead end. If no such U exists, then retreat back to previous vertex W before V and delete the edge from W to V. Okay. unless v is s, in which case we terminate. Okay. So basically we DFS, imagine writing a recursive implementation of DFS, okay, where you start at s. And imagine that in your DFS implementation, whenever you finish a recursive call and then go back up to the parent function call that called it, that corresponds to going back on an edge in the DFS, right? And when I do that, I'll just delete the edge. Okay. And then when I make a call to an adjacent vertex in the DFS, that's my advanced step. And when I reach t, well, I reached t via some sequence of function calls on my stack that started at s and ended in t. All of those corresponded to following edges. And I'm just going to augment along that path. Yeah.
Why do you use the edge? You won't traverse twice, right?
I'm sorry?
Are you going to traverse the edge twice? So you can delete
I don't mean delete it I mean delete, so I mean all of this, which edges are alive and which have been deleted, is all just maintained within the algorithm that computes a blocking flow. I'm not deleting it from the graph or something. I'm just removing it from consideration from this algorithm. Because no, it's a dead end, right? So I mean, in fact, if I'm at some vertex v, and it's a dead end, I can basically delete all the edges that go into v now because I know v is worthless. V cannot be part of an augmenting path from now on, right?
Is that true even after you've removed the first augmented path? Sorry.
Right. So I'm not. Okay. So I shouldn't say augment. Okay. So if v equals t, so what this thing is going to do is it's going to output a flow. Okay, so we want a blocking flow f. So this thing is going to output the flow f. So what I really mean is if v equals t, add to f all edges. Add to f all the edges along the ST path we found. With the minimum capacity, that's right. With the minimum capacity. And then subtract that capacity from everyone on that path. And then delete all the zero capacity edges.
Do you also reverse edges?
No, so we're always going to operate in the same graph L. Okay. So this is just finding a blocking flow in the current residual graph. As we run through iterations of this, we are not changing the residual graph. We are not actually augmenting the flow yet. We're just finding the flow.
So once you augment the flow by the path you found, do you then return to S and start over? Or
Yes. You keep trying to DFS from S.
And is it always true that if you found a dead end earlier and then you deleted a path,
Right.
that will still be a dead end after you've deleted that path?
Right, because we're not actually changing the residual graph, right? We're not actually subtracting this flow from the capacities to define a new residual graph. This is all still happening in the current residual graph. So if something is a dead end, there is no extra capacity that's ever going to leave from it, right? Because we're not reversing anything after it. Like the number, over the various iterations of this, finding paths over and over again, the capacities are only ever going down. Edges are only disappearing. So if there wasn't a path from V to T now, there won't be one in a later iteration.
Couldn't something be a dead end because all of the outgoing neighbors have already been touched in the DFS, but aren't, right, like, well,
So I mean, just think of DFS as how should I put this? Right, but okay. So the point is, if if t is actually reachable, right? If t is actually reachable, we will find a path that goes to t, okay? And then we will saturate, I mean, here we're in a unit capacity case, we will saturate those edges. And then all these other edges are now blocked. So I don't know if I'm answering your
Maybe I'm just getting confused, but what does it mean for something to be a dead end? I thought it means in some cases, well, it could mean that there's just no outgoing edge, but it could also mean that there are outgoing edges, but the vertices at the ends of those edges have already been touched in the search.
Wait. Oh, wait. So first of all, we're working in the level graph, right? Which means edges only go to one level in the future. There are no cycles in L. Oh, maybe that answers your question, right? L has no cycles. What you're saying couldn't happen.
Well, not only
Like there.
cycles, but there are no path is going to be better than any other path, right? You can't. The distances along all paths are the same to the same vertex, right?
That's right.
Okay. So you
But
can't.
But the thing you were saying before, where you said, like, I'm at V, and then maybe there are edges leaving V, but they are going to vertices that I already used to get to V, right?
No, well,
Isn't that what you were saying? Like that can't happen because I'm only looking at edges in the level graph. So this level graph is a DAG. Okay.
I don't. I think you answered.
I'm sorry?
You should have commanded vertices like that. But you should kind of flow and then come here to the path again. You see some mark vertices.
I don't know. Well, anyway, so do you both understand? Okay, so let's just continue because we're running out of time here. Okay, good. So rather than spend time understanding how the misunderstanding happened, let's just now people understand. So let's continue. Okay, so good. So so question. So the runtime. So in the unit capacity case, what's the running time? M. Right? Each edge is looked at a constant number of times, right? Because you're going to maybe advance on it at some point. That's looking at it once. If you retreat on it, then that's looking at it a second time, but now you deleted it, so it's gone forever. If you didn't retreat on it, it means that eventually you reached T, which means that you augmented it along it, or you added to flow, to F along it, and then you deleted it, right? So you only look at each edge a constant number of times, which means O of M total time. So this implies O of Mn in a unit capacity. There's another analysis you could do. Yes, that's right. So runtime unit capacity case OMN per blocking flow. So OMN unit capacity for max flow. There's another analysis you could do is you could say, look, so after d iterations, the distance from S to T in the level graph is at least d, right? Because the distance increases in every step. Okay. Which implies if we decompose any max flow each into paths. Each path has length at least d, which implies that there are at most m over d paths. Which implies the max flow in the residual graph is at most m over d. Right? So this implies that for all d, the number of iterations, so forget about this is pretty good. Linear time to find a blocking flow, that's pretty good. But let's attack this other business of the number of iterations. Where did I write it? I think I might have deleted it. The number of iterations it takes to find a blocking flow. The number of iterations of blocking flow we need. How many blocking flows do we need to find? So this implies that the number of iterations of finding blocking flows is at most d and then plus m over d. So once we've had d iterations, we will only have m over d more iterations, right? And this is minimized when d is about root m. And this is at most root m for d being root m, right? Which implies m time per blocking flow, root m iterations. So this implies O of m to the 3/2 max flow. Or you could view it as m times the min of root m and n. In fact, I'm not going to show you here, but it's even possible, maybe I'll put on a p-set or something. It's even possible to say that. Okay. Okay, so how about, okay, one other thing. Unit graph is one where, other than st, every other well, okay, let me just say another thing. So if you look at, for example, graphs like the following, so imagine a graph that has S and T as follows, and then it has two layers in the middle. And all the edges go from this layer to the next. And all these capacities are 1. Where do you see graphs that look like this? I claim if you've taken 124, I claim that there's a problem we reduced to flow, to ST flow. Yeah, max matching in bipartite graphs. So I claim here you can show that in graphs like this, the number of iterations is at most this d plus n over d. Okay? Which implies O of m root n max flow. So in particular, you can find max matching in bipartite graphs in time m root n. Yeah. So if you just used Ford-Fulkerson, you would get, I guess, F star is as big as n, right? So you get mn, but you can actually get m root n using blocking flows. In the last remaining minutes, I guess I won't have time to get maybe I'll do it at the beginning of next time, tell you a little bit about link cut trees. But how about general capacities? Okay, so here the point is there are at most m. So remember we still have augment, retreat, and advance. There are at most m augments. By augment, remember, I don't mean actually changing the residual graph. I just mean adding the minimum capacity of that path to the current flow we're building, to the current blocking flow. Why are there at most m augments? Yeah. Yeah, every augment has a saturated edge, and that edge will be deleted. So every time we do one, we delete the number of edges. There are at most m edges. How long does it take to perform the actual augment? What's the worst case? M? I claim, so when I say perform the augment, I mean we've built up the path, n, right? We've built up this path, and now we're adding flow values along that path. That path has length at most n. So it implies total time for augments is O of mn. How many retreats can there be? M, right? Because when we do a retreat, we delete the edge. That implies that the total time for retreats is O of m. A retreat is just a constant time thing. You delete the edge. So now how about the total time for advances? So the number, so I want to say less than something advances. And this one is a little trickier, I'll just tell you, because we're running out of time. The point is, after every n advances, right? After every n advances, there will either be a retreat or there will be an augment. Right? You can't advance n times without either reaching t or going backwards once. Right? And if there's either a retreat or an augment, one edge is going to get deleted. So after every n advance steps, definitely at least one edge is going to be deleted from either a retreat or augment, which means there are at most m times n advances. Right? So after every at most n advances, some edge is deleted via retreat or augment. So this implies, so this is going to be O of mn. So in general capacities, we have, again, the number of iterations times time per blocking flow This is at most n, we said. This is at most O of mn. So this is O of mn squared time for max flow. And the thing that I will tell you about a little bit next time is that this algorithm for finding a single blocking flow is kind of wasteful, right? Because we started exploring quite a bit. Kind of, how should I put it? Okay, so I'll say more next time. I don't want to try and rush and say things that don't make sense. But the point is, using a nice data structure due to Slater and Tarjan called link cut trees, it's from '83, you can find a blocking flow not in time mn, but in time m times log n. You can do O of m and log n via link cut trees. We'll see that next time. That's due to Slater and Tarjan. Okay. So Slater and Tarjan in '83. So I think that's enough for today. Questions before we depart? Okay, that's it. Thanks.